So for the last part of the talk, I'd like to tell you just a few of the experiments which are ongoing, and at the same time try and give you a feeling for what it is which is unusual about Bose-Einstein condensation. Here's an example. If you, okay, you know what a vortex is. It's a whirlpool. If you pull the plug out of your bathtub, you see water whirling down the drain. That's pretty standard. If you were to put the plug back in the bathtub and the water kept whirling, you would call that very weird. Now, that is what happens with condensates. We don't call it weird, we call it super. See, it's a feature. Because Bose-Einstein condensation is what's called, among its many other properties, it's what's called a superfluid, which means that, like a superconductor, there's no resistance. You can get things going and it just flows and flows and flows and flows and flows. So here, not just yet, Carl, here is a ball of gas. It's a Bose-Einstein condensate. In the intervening 7 years, we've learned how to make them much, much bigger. This has now got about 2 or 3 million atoms in it.
And we changed the color scheme.
Other than that, it's still black and white, right? But that doesn't play. This ball is about 0.2 of a millimeter across. You could see it with your bare eye. It would look very small, but it's a big, physically, human scale thing. Now we set it to spinning. And you can see there's the first of the vortices forming there. That's the first one, and there's another one just starting to come in. What happens is you spin it faster and faster. Little tornadoes, I'm losing my pointer here, little tornadoes are born like, sort of spawned like brand new tornadoes, and they start wandering their way in, and they start arranging themselves into patterns because the individual tornadoes find themselves repulsive. Let's do the next one. So here's a few more. Now we've got 7 of these, and look, you can see there's another one finding its way in. There's another one. Let's do another.
Just taking the condensate and we're just spinning it faster and faster.
Basically, we take the magnetic bowl the condensate is sitting in, and we start spinning it round and round. And there's still more. And now we spin a little faster, and there's some more. And I think we can do even one more yet. Yeah, okay. So this is now, and you can see as it spins, we'll go back to the sequence. It also gets fatter and fatter. And that's because as it's spinning, it's sort of spiraling outward like Jupiter or something like that, so that as it spins, it gets bigger and bigger because it's the centrifugal forces pushing it outward against the bowl, which is holding it in. This is a single quantum mechanical wave with extremely, as we say in my business, non-trivial structure. Around each of these little dots here, the quantum mechanical phase wraps around. I mean, it looks like a pepperoni pizza, but in fact, it's much more regular than that. It's not as tasty. So this is, I think, starts to get at some of the power of the Bose-Einstein condensate. This is an enormous, extremely complicated, but intrinsically quantum mechanical object, which is the size, which is basically something you could see with your bare eye. It takes, what Bose-Einstein condensation does is it takes the mysterious effects of quantum mechanics, usually known to exist only in the scale of the tiniest atom, and magnifies it out to the point where we can see it and almost touch it.
Yeah. And you can see how it's so different. I mean, this is a little cloud of gas that has been spun up, and instead of just a little cloud spinning around, it develops these wild, interesting structures. Okay, so now we're going to talk about another thing that we've been working on, which is changing, think of this condensate wave and changing how that wave interacts with itself. And we've figured out, with a lot of work and getting things really cold, how to make it so that we can change it so it's sometimes quite repulsive, pushing out on itself, and other times we have a knob that can make it feel very attractive. And so one of the interesting things we wanted to do was take it, and so it was so attractive that the equations that describe this say the wave isn't allowed to exist anymore. There's no solution to these equations. And so what we're really doing is taking a quantum wave and suddenly switching it into the region where it's supposed to die off, and look at how it dies. And we got quite a shock when we did that. So here we started out with our condensate, switched it so it's suddenly pulling in on itself. And for the first few thousandths of a second, it just shrank in, which made sense.
It's imploding.
Yeah, it's imploding. It's attractive. But then it exploded back out. So this is just magnified up. These blue things are atoms flying out with fearful energies. Well, a few hundred billionths of a degree above absolute zero. So, in fact, this is the puniest explosion that's ever been observed. But nevertheless, it wasn't supposed to be there. And so this phenomenon, it's the still images of that movie, and you can see the stuff exploding out. And those of you who are familiar with supernovas, where a star runs out of fuel and collapses in on itself and then explodes out, leaving with this giant explosion, then leaving behind some little cold remnant, neutron star or something. See that it's really, I mean, the physics is utterly different, the scale is totally different, but to watch it, it looks very much the same. We see stuff collapsing in, exploding out, and this little cold remnant, but all of this, so it was just cute that it was like a supernova, and that's why we call it a bosonova. But the exciting thing from the physics point of view is, we're seeing something totally unexpected. And this is sort of another manifestation of Bose-Einstein condensation. We can get study material in a totally different regime than people have been able to have material before. And you can find out there really are surprises like this. And of course, this is what experimental physicists die for, is something where you got surprises, especially if theoretical physicists predicted that it wasn't supposed to happen. So, so these give you a little bit of the flavor of the fun we're still having playing with Bose condensates now.